Ever wondered how your banking app, or any complex software really, keeps your data safe, even when things go completely haywire? Well, the secret, for decades now, has been this incredibly powerful concept called a transaction. They are truly the unsung heroes of reliable software. So let's dive in and see exactly how they work.
So first up, to really get why transactions are so important, we have to understand the problem they're built to solve. You see, in the real world of data systems, it's not a matter of if things will go wrong, it's a matter of when.
And believe me, the list of potential disasters is long. Hardware can fail right in the middle of an operation. The application itself can crash. The network can just drop out. You could have multiple people trying to change the exact same piece of data at the same time, literally overwriting each other's work. Or you might try to read some data that's only halfway updated. It's a pretty chaotic environment. And without a solid plan, it just leads to corrupted data and, you guessed it, very unhappy users.
So how in the world do we bring some order to all this chaos? Well, for decades, the best answer we've had is transactions. You can think of them as a safety net for all of your data operations.
Okay, so what is a transaction? At its core, it's just a way to group a series of actions, reads and writes, into a single logical bundle. And the crucial idea here, the most important part, is that this entire bundle is treated as one single operation. It's a real all-or-nothing deal.
And because of that, every transaction has only two possible outcomes. It can commit, which means everything inside that bundle succeeded, and all the changes are made permanent. Or, if absolutely anything goes wrong, it will abort. And that means the database completely throws away or undoes all the changes made inside that transaction. It's literally as if it never even happened. This is what frees up the application developer from having to worry about partial failures.
Now, these safety guarantees are famously summed up by an acronym you've probably heard of: ACID. It stands for atomicity, consistency, isolation, and durability. Let's break down what each of these really means, because they're all super important.
First up, we've got atomicity. And this is really just that all-or-nothing principle we were just talking about. If any part of the transaction fails, I mean anything, maybe the network drops, maybe the disk is full, the entire thing is aborted, and all of its writes are rolled back. You could almost call it abortability. It's what saves you from being left with a partially updated, inconsistent mess.
And this diagram just shows it perfectly. Let's say user 1 is trying to perform two related updates. The first one goes through, it succeeds. But then, right after that, something goes wrong. An error, a timeout, doesn't matter what. Without atomicity, that first write would be stuck there in the database, leaving everything in an inconsistent state. But with atomicity, the database just says, nope, the whole transaction failed, and it rolls back that first write, keeping all your data clean and correct.
Okay, what about the C for consistency? Now, this one's a little bit different. It just means that the data must always be in a good state according to your application's own rules. For instance, in an accounting system, debits and credits must always balance out. But here's the catch. The database can't possibly know your specific business rules. So consistency is really the application's job. The database just gives you the tools, like atomicity and isolation, to help you get there.
Next is I for isolation, and this one is a really big deal. See, most databases have lots of users and processes hitting them all at the same time. Isolation means that even though all these transactions are running concurrently, they're protected from interfering with each other. It creates this illusion that each transaction gets to run all by itself, in its own little bubble, one after the other.
And this slide right here shows you exactly what happens when you don't have isolation. This is a classic race condition called a lost update. So you have two users trying to increment the same counter. Both user 1 and user 2 read the current value, which is 42. Both of them add 1 to it in their own process, getting 43. And then both of them write the value 43 back. The final result should have been 44, right? But because they weren't isolated from each other, one of those updates was completely lost. This is exactly what isolation is designed to prevent.
Finally, we have D for durability. And this is really the ultimate promise of a database system. Once a transaction is successfully committed, that data is safe. It's not going to be forgotten even if the power goes out or the hardware completely fails. Usually, this means the data has been written to something non-volatile, like a hard drive or an SSD.
But here's a little dose of reality. Perfect 100% durability is kind of a myth. Your SSDs can have firmware bugs that cause data loss when the power is cut. A massive power outage could, in theory, take down all of your replicated servers at the same time. Data can even just silently corrupt on a disk over many years. So,
While durability is a very strong guarantee, it's always wise to have multiple layers of protection, like good old-fashioned backups.
Okay, let's circle back to isolation for a minute. Because in the real world, it's not a simple on or off switch. It's more of a delicate balancing act, a trade-off between performance and correctness, and there are actually different levels of isolation you can choose from.
So to understand why this is a trade-off, just ask yourself this question. Imagine you're running a huge report that takes, minutes or even hours to complete. What happens if, while your report is chugging along, other users are busy changing the very data that you're trying to read?
Well, you can get this classic problem called read skew. In this example, Alice has 2 bank accounts, each with $500, for a total of $1,000. Now, a separate transaction is right in the middle of transferring $100 from account 2 to account 1. Alice's query happens to read account 1 before the transfer arrives, so it sees $500. Then it reads account 2 after the money has already been sent, so it sees $400. To her, for a brief moment, it looks like $100 has just vanished into thin air. It's a temporary inconsistency, but a very real and confusing one.
A really elegant solution to this problem is something called snapshot isolation. The idea is brilliant, actually. When a transaction begins, it's given a snapshot of the database as it existed at that exact moment in time. Then, for the entire life of that transaction, it will only ever see that frozen-in-time version of the data, completely unaffected by any changes that happen later.
So how does this magic actually work? Well, the database uses transaction IDs. When your transaction starts, it gets its own unique ID, and it can see a list of any other transactions that are still in progress. From there, the rules are pretty simple. It ignores any writes from transactions that were already running when it started, and it ignores any writes from transactions that start after it. It only sees data that was already fully committed before it began. And this is so cool because it allows long-running reports and fast writes to happen at the same time without blocking each other.
So the crucial point in all of this is that these aren't just abstract computer science concepts. They represent very real-world trade-offs that engineers have to make between performance, complexity, and of course, safety.
And this quote from our source material really just sums it all up perfectly. The truth isn't simple. Just like any other technical choice, transactions have huge advantages, but they also have limitations. There's no single best answer for everyone. Weaker isolation might be faster, but it opens the door to subtle bugs. Stronger isolation is safer, but it might slow things down. The key is to understand the guarantees your system is actually giving you.
Which leaves us with one final thought to chew on. We all build and use applications that rely on data being correct. So the question to ask yourself is, do you really know what safety guarantees your database is providing? Understanding transactions is the absolute first step to making sure your software isn't just fast, but is truly, genuinely reliable.